Thank you for coming to my talk. I hope everybody hear me well. So today I'm Moussa Taifi. I'm a senior data science platform engineer at Zender at AT&T. We are the advertising arm of AT&T. We do around processing maybe around between 100 and 200 terabytes of data per day. And we serve around between 40 to 50 billion ad impressions per day. But this is not what I'm here to talk about. I'm here to talk about more like in a preaching way of coming to you with examples of something that's called clean machine learning code. So I would like to start with a story time. It's a smelly one. I just had a child recently. It's very smelly kind of story time. So this is a capable junior machine learning engineer with 2 years of experience that started working at, let's say, a medical insurance company. So he comes in first day. He inherited this insurance prediction pipeline that predicts optimal premiums for members. Management comes to him and tells him, oh, you know what we need to do today? We need to change the model from a logistic regression model to a gradient boosted tree model. Because offline, the boosted model works better and dollars. So let's see what he's gonna find throughout his journey during his first onboarding. So he clones the project. So he's like, Git, yeah, this is a great company, I love it. So we dodge that bullet. Second thing he finds is that he's looking for some tests folder in that project, and he finds some notebooks laying around to test the code manually. This smell is called viscosity of design. Then he finds that the notebook unit tests take around 1 hour to complete. This is called viscosity of environment. He ventures, he's like, okay, I'm gonna try to change one name in the loss function tests. And he finds that he needs to change that name in 6 different places, which is like a rigidity problem. Next, he gets one related test on the gradient calculation problem, and he finds that he broke something on the test data generating code. That's called fragility. Then he tries to reuse a small function from the gradient calculation, and he's like, I don't know. I don't trust this code enough. So he's immobilized. And finally, he finds a variable names like OVH underscore V5, and he's like, you know, what did I sign up for? This is not what they was advertised on the company website. So it's a little bit of anecdotal story today, but really I wanted just to, it's dear to my heart to talk a little bit about this clean code, how to raise the awareness of what do we do here as data scientists and developers, Python developers, and how do we raise this awareness so that we know why do we care about this cleanliness, this craftsmanship sort of spirit. It's because, honestly, the problem is either it will be what you're building, what data scientists are building, is either going to be costly or dangerous or even deadly sometimes. We depend on software every day for everything. Your grandma, my grandma, she's buying stuff on some insurance website. She's interacting with software all the time. Also your car, your gas pedal is not connected to the brakes directly. There is a processor in between. The airplane, same thing. You have a processor in between the button that the pilot is pressing and the actual thing that's gonna make this airplane land. Same thing. We've seen self-driving car hitting pedestrians. There's gender bias on large-scale translation systems. You think that fingerprint on your phone will save the day, but then they're like, oh, you know what? Your screen protector counts as a fingerprint. And then you have smart system making bad decisions like, Knight Capital, for example. And like another thing that people don't realize with this new field of machine learning is that really almost 40% of data scientists and ML engineers, have less than 5 years experience. And the problem is that there's not enough mentors and teachers. And this new cohort, this energetic, young, let's do it, let's deploy, let's ship it, are bound to repeat errors of old cohorts, which is not their fault. I mean, they're trying their best to ship something, but this talk is really try to bring back some of the history lessons that software engineering brought along throughout the years, and advertise them a little better. We have this. They're dealing with this boom of integration problems, and basically the goal is to bring the experience of building complex systems to the machine learning community. So some books that you'd be interested in if you're starting out and discovering this: Robert Martin. So Uncle Bob has a nice 2 books that are very nice. We have Clean Code and Clean Architecture. And what I try to do in this talk is to really take the concepts that he has there related to software engineering and try to, every time I see software development, software engineering, I plug in machine learning engineering to see how changing some words really raises the awareness. And there he has 2 main goals that we're trying to do here, right? So if you need to sell this to yourself, is you have clean code reduces the cost of change of your machine learning pipelines. So that's the first one. So cost of change. And then it increases the optimal responsiveness of change of your machine learning pipeline. So in a graphical form, you can see this. This is what's going to happen to your, this is what happens to machine learning projects across time. So on the bottom axis, you have time, and then you have 2 axes on the left and the right side. I might be preaching to the choir, but it's definitely interesting to see. You want at the same time optimal cost of change. You want really low cost of change, and at the same time you want really good optimal responsiveness. But unfortunately, as time passes, the red line, so the responsiveness to change, decreases. And at the same time, your costs increase. So this is like a visual sort of, if you have to sell it to yourself. And then the difference between the cost of change and the actual costs that you're seeing after 1 month, after 6 months, after a year of you maintaining these pipelines, you see the costs slowly increasing, and it's called technical debt. So I had some practical principles for you today that would help a little bit with this. And it's these 5 ones that I wanted to, it helps you build vocabulary so that when you're talking to your teammates, you can actually talk with similar vocabulary. So you're not just saying, oh, this is too complex, oh, this is difficult, oh, this is too costly. You want a little bit more fine-grained vocabulary. So we have loose coupling, high cohesion, change is local, easy to remove, and mind science components. Let's talk about loose coupling. Loose coupling is basically when you have 2 machine learning components that use each other. And the less ML components know about each other, the looser they are. So more truism, just like. But the key is that the less coupled machine learning components are each other, the easily changed and easily replaced they are. So here on the left we have a picture. We have a tightly coupled, loosely coupled system where you have data ingestion, feature engineering, model training, and model selection are just stepping on each other's feet, importing each other all over the place. Trouble. When you try to decouple these systems, you end up with a more sort of non-cyclic system where you have loosely coupled components. So that's the first one. Second one is high cohesion. High cohesion, when you want to talk about your system and tell them, you know, this design gives us better high cohesion, is where you want your components that change for different reasons or at different times, they should be kept separate. It's a partitioning guideline. You have a component, and inside of the component, stuff changes for different reasons. You have low cohesion. The third one is change should be local. Okay, so most of the cost of machine learning pipelines is really during the maintenance phase. We need to change this, we need to update that, we need to do this. And the more local your change is, the better. And so you really want, like, it's an exercise in dealing with boundaries. When you have like clear boundaries between components, then change is local. Okay. The fourth one is it is easy to remove. I like this one because we are at PyData. I've been a couple talks that really advertise a bunch of tooling that we rely on every day from some great open source and commercial people. And so the key here is that those it's like a favorite of Uncle Bob is that they are all details. Okay, TensorFlow, PyTorch, scikit-learn, MySQL, Hive, EMR, Airflow, Kubeflow, Dask, Pandas. Did I say Pandas is a detail? Yes, I did say Pandas is a detail. NumPy is not what you are paid to do. The business logic, really the jewels of your business are not to use the time series component of Pandas or the DAGs elements of Kubeflow or whatever. They are details. This whole idea came from the fact that sometimes in those books, even the web, so the web itself is a detail. It's not your application. It's a delivery mechanism. Nothing else. The database is a detail. It's kind of controversial. You might be like, what is this crazy man talking about? But really, like when you think about it, your manager, your bottom line does not depend on like which database you're going to be using, which JavaScript framework you're going to be using. It's really like the core business logic. And so these principles here are here to help you protect your business logic from the outside components that you need to use, but you want to use them in a respectable, like a guided manner, so that you don't have to deal with. You're not at the mercy of frameworks. One nice thing that sometimes is mentioned in these books and talks is that framework managers, love it when you use their processes, their libraries, and really, it feels like every time you depend more and more on a framework, the more you are part of this. I don't want to be too controversial, but it feels like a harem, a little bit, of where they don't depend on you at all, but you depend on them so much. And throughout the years, there's a way to figure out whenever they will change something in their framework, make sure that it will hurt them more than it will hurt you. It's a very specific thing. So, okay, so that's the preaching. The fifth one is just that it's mind-sized components. I don't think that you can think about 300 components bunched up in one thing. So mind-sized component is that you want to be able to test a component in isolation. Really, in a guideline, you don't want to have to load up the web server, the database, the browser, have a pipeline upstream that you need to be able to test a specific piece of your code. Might be hard. It's pretty hard to do it, but that's the moral center of this clean code architecture kind of is that you want to strive towards it. Obviously, engineering you can't achieve it 100%, but definitely you want to strive towards that isolation, being able to test in isolation. So now let me shift gears to some actionable items. We have throughout the years, like software engineering came up with a bunch of software design principles that can be applied to you. They are very focused on object-oriented programming, which is kind of like the best we have, one of the best frameworks of thought we have about software. And they came up with this solid software architecture. So they've been around for a while. I think I'm doing my job to actually raise the awareness about them again and again, so that newcomers, people have like 1 year, 2 years of experience, they never saw them before, could see them again. They have nice names. You have single responsibility principle, open-close principle, Liskov substitution principle, interface segregation, and dependency inversion. Let's go through them. We have a blog post about this, how it applies to machine learning. Here I might be going a little too fast, but I invite you to read our blog post to figure out, how to start exploring how can I use some of these techniques to protect myself and my software, my company from external, upgrade of this and this is not supported anymore and stuff like that. So the first one I wanted to talk is the single responsibility principle. Single responsibility principle is basically you have a machine learning component, class, function should have one and only one reason to change. You want a single actor that's interested in this function and that will generate change for you. So here, for example, we have a class called ML model, has a fit partial, has transform features, and has publish metrics. Now, it's very easy to add things to your class because I might need this, I might need this. But when you think about who's the actor that will use this and will trigger changes, so if the database changes, if the schema changes, then your transform features will change. If you switch from CloudWatch to some Prometheus, then publish metrics is gonna change. So you want to really split this up into pieces that are manageable. Next one I have is the open-close principle, which is kind of my favorite principle, which is you should be able to extend the behavior of machine learning component without modifying it. What do I mean by here? So here we have an example of, at the top, you have model manager on the top right. That previously was used in simple featurizer, and he's happy to use it. We have a new request to improve the model. We need a new featurizer. We're gonna try to use the super featurizer. Unfortunately, the super featurizer has a completely different interface, which means that model manager can't use it. So model manager comes in, your method of doing it is okay, the naive way of doing it is just gonna copy that code, put it there, and hard code everything just to get it work. The more experienced way is okay, I'm gonna protect myself against this change in future versions. And by doing that, you try to abstract away the featurizer in an interface or an abstract class, and then suddenly the model manager is able to swap in these strategies as nicely as possible. And then, next week, 2 weeks, next sprint, somebody comes, different featurizer, bam, you can stick a super duper featurizer. So this is called open-close principle. We were able to extend the functionality of Model Manager without modifying anything inside the Model Manager. Yeah. So this called principle, I don't have an example today. But the interface segregation principle is kind of very interesting as well. You have, the goal here is to make fine-grained machine learning component interfaces that are client-specific. You don't want, here we have an image featurizer, we have a text featurizer, a row featurizer, and all of them depend on this data generator, this magical class that does everything. Which means that even if the image generator only cares about, image featurizer only cares about gen images, image featurizer might have to change if data generator gen text changes. I mean, well, that's like a no-no. So what we try to do is that we try to really specialize the interface that data generator will provide so that image featurizer does not have to know too much. It only needs to know exactly what it needs. So that's called interface segregation principle. The next one is the dependency inversion principle, which tells you in a way to depend on machine learning pipeline abstractions, not on machine learning pipeline concretions. What do I mean by that? I mean, let's say we have a model trainer again that we did a good job at like having interface model builder, so that we build a model before we run the fit function, for example. But the problem here is that there is like an intrinsic problem there, is that the model trainer still needs to know about tensor model builder implementation. So every time we change something in tensor model builder implementation, model trainer needs to adapt as well. One of the patterns of inverting this dependency is by using dependency injection, which in a way here it's like one way of doing dependency injection where we have an assembler, like your main process, your main function, that does this assembling and this wiring, so that you can build you first create a model trainer, and then assembler creates a model TensorFlow model builder implementation, and then injects it inside the model trainer, and the model trainer is able to use the common interface. This one is a little bit more abstract, but definitely the goal is like, am I depending on concrete, like fine-grained, low-level policy, or am I depending on high-level policy? Here, model trainer now only depends on high-level policy, which is the interface. So those are like the 5 sort of solid principles. I invite you to look them up again later. Obviously, all of this works when you have like a test-driven machine learning. And the only thing I wanted to say here is that it really increases the trust that the developers have in your code base. The more tests you have, more coverage you have. And what I wanted to emphasize, it's not reserved to established software engineering components, but can be applied to machine learning components as well. So I try to bring 2 worlds together. There is the machine, I think some of you might be familiar with the hidden high interest rate of machine learning technical debt, which is a nice paper from Google, from D. Scully, which deals with really trying to define some of the machine learning technical debt that we see in the wild, and how they relate to these principles. So here I cover 4 of them. So you have entanglement and glue code is one technical debt symptom. Also, this vocabulary is useful for you to explain to someone that we have this problem or that problem. Second one is hidden feedback loops. Third is undeclared consumers. And the fourth one is pipeline jungles. So I try to figure out the mapping between our principles that we've seen in this one. So the first one is entanglement. What's entanglement is that inherently inside our ML code, you are combining, software, regular software, if, loops, objects, but at the same time you're combining that with data, and it's an intrinsic part of your code. And so when you have both of these coming together, they're deeply intertwined. And then as soon as you have that, then you start noticing that people start adding glue code, which is code that has no real functional utility except moving data from one part of the system, converting it to another format, and then feeding it to the machine learning, like prediction training. And so when you see glue code or entanglement, that's a violation of the single responsibility principle. Next one is hidden feedback loops. Hidden feedback loops is pretty neat. It's such a weird realization that your deployed models in production will change future training distribution. So your customers interact with your code, with your API, and then they react differently, so they generate a different training distribution. And so what happens is that you need to retrain your model. And by retraining your model, what you effectively, coming from like a traditional software engineering, is that you're allowing users to rewrite if statements in your model. That's literally what if left unchecked, you're letting your users to reach inside your code, which is this machine learning model, reach inside and change the code inside your machine learning model. And it's like an overreach, really. And so you start having data validation, things like that, to catch any drastic changes. But you're noticing that your machine learning model is open for modification by like an unknown external source, which is kind of should be scary for any machine learning practitioner that actually makes money or loses money from or deals with lives. But even further is that you have hidden feature feedback loops, which are these features that you can't even detect fast enough, like weekly, like monthly sums. They adapt really slowly to any changes because they deal with the moving window of features. So that's for the OCP. The third one is this undeclared customers. Undeclared customers, I think it's easier to understand. It's like you have an API, and billing is using this API. They're getting it. They're figuring out every day how much money did we spend, how much money did should we bill our customers, for like a month. Everything is good, and then you get a report from HR that also uses this API. You didn't even know that they were using this API, and they're asking you for changes. They're asking you to change the API that you built for billing. So, what do you do? What do you do in that case? They're like, oh, we like this machine learning model. Predicts how much billing is going to happen. So something in HR actually now depends on it. This is a sign that the API design has this problem of is not segregated enough. That we do not know. We need to be able to shrink the surface area of API so that the consumers that are with us, are not they don't sprawl. And the interface segregation principle helps with that. The fourth one is pipeline jungles. Pipeline jungles is is an unfortunate reality. We have pipelines basically operate at the lowest abstraction, which means that they are the ones that are moving data from point A to point B. They are the ones who trigger the training. They are the ones that trigger the batch inference. And so since they are like, they depend on like low-level concretions, people just, like to make that as simple as possible. And so the dependency inversion principle suffers there, where you are depending your code, your pipeline code, now depends on exactly like raw concretions of some implementation, which really can damage your software. And now a data scientist comes in and they're like, okay, we need to upgrade this thing here. What they do is that they go potentially and start torturing this code by adding experimental code paths. So experimental code paths are a sign that you have too many pipeline jungle. You have a jungle of if-else statements that say, we're gonna try this model on user IDs that modulo 10 equals 0, send that much traffic to this model. And so we have a bunch of experimental paths. Obviously, projects evolve, and then we end up with dead experimental paths. Experimental paths that nobody cares about anymore, but they're there. And it's a sign that your main control flow has a problem with too many responsibilities. And how the hell did they figure out that they are able to even change this code? They should be able to extend it with external modules, external plugins, but they shouldn't be able to go directly in the main control flow and add an if statement. So the experimental, because it's fast, it's easy, people just add it. So you want to remedy this with shrinking the API that you're providing, shrinking the partitioning the responsibilities of each part, making sure that you cannot change code and only extend it, and also whenever something knows too much, it's time to reverse the dependencies. So I try to put them here as a little bit better format. If you see something, you have ML problem, you have entanglement or glue code. That means that usually it's related to entanglement. As soon as you change one variable in one place or one calculation, like you're doing, instead of using 7 days in a week, you're only using business days, so 5. Now everything, the change just impacts everything downstream. That's a symptom of violating the single responsibility principle. Sometimes you have these God classes that just have thousands of functions, or even just hundreds of functions. There's no need for bunching a bunch of functionality inside. So the third one is hidden feedback loop. So you have baggage of hidden functionality and the realization that your customers are able to directly impact your models. Undeclared consumers is when you have unknown clients piggybacking on generic interfaces. That's a violation of the interface segregation principle. And then you have pipeline jungles, which really we need to depend on more abstract layers. Okay. Here it's more like a call to action. The future of ML engineering is really sort of, I don't want to doomsday, but it's really definitely what happens usually in this kind of industries is that you have a continuous flow of machine learning engineers, and then there's one deadly machine learning pipeline, God forbid, some plane crashes inside of a stadium, And then legislators are like, oh, wait a minute. This is crazy. Who are these developers that have built this thing? Who are these data scientists that were, they lost, basically what they're gonna think that they lost control of their software. I mean, I believe that we are, reasonable people and really like honest. But if legislators believe that we lost control of our software, that we don't know what we're doing, then their normal reaction is that legislators will need to take action by creating laws. Then laws. When was last time you had to deal with a law that some of you might be already in like the healthcare environment where you have to abide by a bunch of laws. But the problem with these laws is that they are made by your House representative person, your congressman, your city council guy, which makes it kind of unbelievable that someone that has no idea what software is, what software engineering was, what machine learning is able to set up rules of you can only git commit on Tuesday at 4 p.m. You can only deploy once a quarter. All your deployments have to be signed by the mayor. You cannot deploy anything without approvals. And this is just, I'm trying to raise the awareness so that we're aware that this might happen. That's pretty much it. I have some references in there. I have 2 plugs. Sorry about that. We're hiring. You have Xander Data Science Platform Engineering. Go to this link if you're interested. Also, I organize a New York algorithms coding practice group sometimes on Meetup. So come in if you want to learn about how to do, all path, shortest path. And that's pretty much it.
Questions, anybody?
Really interesting talk. Thank you for this. How has this worked out in practice at AT&T?
Sorry, what? Yes.
Yeah. How has this worked out in practice at AT&T? Are you educating your data scientists with all of these principles? Are people lapping it up in practice? Do you see increase in code quality? How do you measure that?
Right. Yeah. How do you measure your quality? The quality of your software. You use. Well, this is all engineering, right? So it's this is goals we want to go towards, and you find that you have 2 camps. You have 2 camps of developers. You have developers that care about their software. They care about what they do. They do it because they like building software. They like the abstractions. They like, and then you have coders that don't care. They are there for the paycheck. And a good example is open source software. Sometimes you find open source software much better than internal software, because people open source they really they do it. The motivation is so much more morally elevated, I want to say, and so that's I mean these opinions are mine, so they're not related to my employer at all, but definitely the seniority, it just felt like some of these concepts, we focus on the libraries, we focus on the frameworks, but we don't focus on the history of software engineering. The 50s, 60s software, people that are mature, they came in from accountants and then they built all these base things that we still use today. They knew what deadlines were, what sprints were, and then since it became so interesting, software engineering, you double every 5 years, you double the number of software engineers. Same thing's happening for ML engineers. You have someone that's been a software engineer for 20 years, and then they switch to ML engineering. They bring with them so much implicit knowledge. But you have an ML engineer that came out from a boot camp, very energetic, but they missed these principles, this sort of methodologies that really help move business forward in a nice, sustainable way. So you have these two camps. I hope it's like an example. Yeah.
You didn't talk about Jupyter Notebooks, so.
Right. Sorry, we have a question here. Oliver, to the microphone.
Sorry. Thanks. You had mentioned the undeclared customers and narrowing like who you're giving the data to.
Yeah.
How do you balance that with duplicating data all over the place and duplicating like business logic across like too many teams if it's very similar?
Right. Yeah. In a way, like I don't know. I think Kate Beck or somebody before said that all design is striving towards deduplication. Basically, like, so it's a little. I don't know if it's like it's true or not, but definitely deduplicating. And so what you're asking is like, how do we create interfaces that are specific to customers without creating the duplication of data or functionality or what, I'm not sure
Like
what.
data and logic.
Data and logic, yeah. Well, I mean, with this interface segregation principle, you're not duplicating data per se. Like you're duplicating how the data, how the API calls are managed from like a unified source, but we only target a specific set of customers. I don't see if I'm not sure if we can talk offline. Not sure how this duplication happens. Yeah. Sorry. Yeah. So Jupyter Notebook.
Yeah, I was just going to ask if you have written anything or have some experience about the utilization of Jupyter Notebooks in the pipeline. So, often when I come across somebody with significant engineering background, they sort of, dislike Jupyter Notebooks, but Jupyter Notebooks are a fixture kind of in the data science pipeline.
That's right. Yeah, Jupyter Notebooks are, they're like so easy to use that data scientists really love them. And then you take notebooks and then you want to bring them to production, and it creates like problems when you have to scale your software. I'm still trying to wrap my head around it. Obviously, you can see like violating a bunch of rules here because I guess the idea there is to be able to train your data scientists to iteratively raise the abstraction level of their software. So notebooks are not bad. They just need to be coupled with some IDE, PyCharm, some other IDE that will have like a dance between the two, where you start your exploration in Jupyter Notebooks and then you promote code to a more stable sort of repo, and then I'm even thinking like you explore in Jupyter Notebooks and you start writing unit tests. You use your Jupyter Notebooks to figure out how to pass those unit tests. Then you take code and place it in like a nice tested place, and then you refactor your code, and you're able to import stuff in Jupyter Notebooks so that you can continue this exploration. I think I'm still grappling with this problem, but yeah. So definitely there is a dance between Jupyter Notebooks and more established IDEs. Yeah.
All right, thank you so much.